Hello, my name is Shabsin and welcome to my channel. So today we will learn about the graph. In the previous video we have learned about the types of tree, the trees, the stack, the queues, and today we will learn about graph. So in the beginning I am saying that it will be a very lengthy video because graph is also a very vast topic. Okay, so focus on this video and please kindly concentrate. So let's begin. So what is a graph? A graph can be defined as a group of vertices and edges that are used to connect three vertices. A graph can be seen as a cyclic tree where the vertices nodes maintain any complex relationship among them instead of having a parential relationship. Okay. So coming to the directed and undirected graph, a graph which we can say G represent, which we are representing graph as G can be defined as an ordered set GVE, where VG represents the set of vertices and EG represents the set of edges which are used to connect these vertices. So coming to the this is an example of undirected graph. Okay, because it is we can see that its edges are not attached with any of the directions. If an edge exists between the vertex A and B, then the vertices can be traversed from B to A as well as A to B. And in directed graph, edges from an ordered pair. Edges represent a specific path from some vertex A to another vertex B node. A is called initial node while the node B is called terminal node. Now coming to the graph terminology. What is a path? A path can be defined as the sequence of nodes that are followed in order to reach some terminal node P from the initial node U. Then the closed path. A path will be closed as will be called as closed path if the initial node is same as the terminal node. A path will be closed path if V0 equals to V to the end. Then coming to the simple path. If all the nodes of the graph are distinct with an exception V0 equals to Vn, then such path P is called as closed simple path. Then coming to the cycle. A cycle can be defined as a path which has no repeated edges or vertices except the first and the last vertices. Then coming to the connected graph, a connected graph is the one in which some path exists between every two vertices UV in V. There are no isolated nodes in connected graph. Then coming to the complete graph, a complete graph is the one in which every node is connected with all other nodes. A complete graph contains n-1/2 edges where n is the number of nodes in the graph. Then in a weighted graph, each node edge is assigned with some data such as length or weight. The weight of an edge can be given as WE, which must be positive value, indicating the cost of traversing the edge. Then comes a digraph. A digraph is a directed graph in which each edge of the graph is associated with some direction and the traversing can be done only in the specified direction. Then coming to the loop, an edge that is associated with the similar endpoints can be also called as loop. Then finally the adjacent nodes and the degree of the node. So first is adjacent node. If two nodes U and V are connected via an edge E, then the nodes U and V are called as neighbors or the adjacent nodes, right? So coming to the last part, that is degree of the node. A degree of a node is the number of edges that are connected with that node. A node with degree 0 is called as isolated node. Now coming to the graph representation. So a graph is a data structure that consists of set of vertices called nodes and edges. There are two ways to store graphs into the computer's memory. First is sequential representation, which can say adjacency matrix representation, and the second one is linked list representation, which we can also say that adjacency list representation. So in sequential representation, there is a use of an adjacency matrix to represent the mapping between vertices and the edges of the graph. We can use an adjacency matrix to represent the undirected graph, directed graph, weighted directed graph, and weighted undirected graph. In adjacency matrix of I and j, W it equals to W. It means that there is an edge exists from vertex I to vertex j with date W. An entry Aij is in the adjacency matrix representation of an undirected graph G will be 1 if an edge exists between Vi and Vj. If an undirected graph G consists of n vertices, then the adjacency matrix for the graph is n by n cross n. So the matrix will be A equals to Aij, can be defined as Aij equals to 1 if there is a path exists from Vi to Vj and the Aij equals to 0. Otherwise, it means that in an adjacency matrix equals to 0, 0 represents that there is no association exists between the nodes, whereas 1 represents the existence of path between two edges. Okay. So this is the diagram which this image shows that the mapping among the vertices A, B, C, D, E, and this mapping is represented by using the adjacency matrix. Okay. So there exist different adjacency matrix for the directed and undirected graph. In the directed graph, an every Aij will be 1 only when there is an edge directed from Vi to Vj. Now coming to the adjacency matrix for a directed graph. In a directed graph, edges represent a specific path from one vertex to another vertex. Suppose a path exists from vertex A to another vertex B, it means that the node A is the initial node, while node B is a terminal node. So consider the below directed graph and try to consider this graph, directed graph A, B, C, D, E. In this graph, we can see that there is no self loop, right? So the diagonal entries of the adjacent matrix are 0. Now coming to the adjacency matrix for a weighted directed graph. It is similar to an adjacency matrix representation of a directed graph, except that instead of using the 1 for the existence of a path, here we have to use the weight associated with the edge. The weights on the graph edges will be represented as the entries of the adjacency matrix. We can understand it with the help of an example. Consider this below graph, right? So in this image we can see that the adjacency matrix representation of the weighted directed graph is different from other representation. It is because in this representation the non-zero values are replaced by the actual weight assigned to the edges. Adjacency matrix is easier to implement and follow. An adjacency matrix can be used when the graph is dense and number of edges are large. Though it is advantageous to use an adjacency matrix, but it consumes more space. Even if the graph is sparse, the matrix will still consume the same space. Now coming to the linked list representation. The adjacency list is used in the linked representation to store the graph in the computer's memory. It is efficient in terms of storage as we only have to store the values of edges. So in this figure we can see there is a linked list, okay, or adjacency list for every node of the graph. From vertex A there are paths to vertex B and vertex D. These nodes are linked to nodes A in the given adjacency list. So an adjacency list is maintained for each node present in the graph, which stores the node value and a pointer to the next adjacent node to the respective node. I must say that if all the adjacent nodes are traversed, then store the null in the pointer field of the last node of the tail. So now coming to the BFS algorithm. Okay. So what is a BFS algorithm? BFS algorithm or breadth first search is a graph traversal algorithm that starts traversing the graph from the root node and explores all the neighboring nodes. Then it selects the nearest node and explores all the unexplored nodes. While using the BFS for traversal, any node in the graph can be considered as a root node. So I can say that there are many ways to traverse the graph, but among them BFS is the most commonly used approach. Okay. So it is a recursive algorithm to search all the vertices of a tree or graph data structure. BFS puts every vertex of the graph into two categories, visited and non-visited. So coming to the applications of a BFS algorithm now. BFS can be used to find the neighboring locations from a given source location. In a peer-to-peer network, BFS algorithm can be used as a traversal method to find all the neighboring nodes. Most torrent clients such as BitTorrent, uTorrent, right? You guys are using torrents, so you must know that BitTorrent, uTorrent are the torrent most example of famous torrent clients, and employ this process to find seeds and peers in the network. You will see that if you are downloading a video from torrent, BitTorrent or uTorrent, you must see that there is a seed peer, right, connection. The BFS can be used in a web browser to create web page indexes. It is one of the main algorithms that can be used to index web pages. It starts traversing from the source page and follows the links associated with the page. Here every web page is considered as a node in the graph. BFS is used to determine the shortest path and minimum spanning tree. BFS is also used as Shaney's technique to duplicate the garbage collection. It can be also used in Ford-Fulkerson method to compute the maximum flow in a flow network. Now coming to the algorithm. The algorithm is as follows: that set status equals to 1, which is the ready state for each node in G. Then enqueue the starting node A and set its status equals to 2, which will be the waiting state. Then repeat the steps 4 and 5 until Q is empty. So dequeue a node N, process it N and set its status equal to 3. This is the process state. The step 5 will be enqueue all the numbers of names that are in the ready state whose status equals to 1 and set this status equals to 2. Waiting state, end of loop, exit. So these are all the algorithms, right? So coming to the DFS algorithm. So DFS algorithm is also known as depth first search algorithm. So the depth first search algorithm, first it is a recursive algorithm to search all the vertices of a tree data structure of the graph. The DFS starts with the initial node of graph G and goes deeper until you find the goal node or the node with no children. So because of the recursive nature, stack data structure can be used to implement the DFS algorithm. The process of implementing the DFS is similar to the BFS algorithm. So step-by-step process is to implement the DFS algorithm is given as below. First, we have to create a stack with the total number of vertices in the graph. Then we have to choose any vertex as the starting point of traversal and push that vertex into the stack. After that, push a non-visited vertex, which we can say that adjacent to the vertex and on the top of the stack to the top of the stack. Now repeat steps 3 and 4 until no vertices are left to visit from the vertex on the stack top. If no vertex is left, go back and pop a vertex from the stack and repeat steps 2, 3 and 4 until the stack is empty. So coming to the applications of DFS algorithm, DFS algorithm can be used to implement the topological sorting. It can be used to find the path between two vertices. It can also be used to detect cycles in the graph. DFS algorithm is also used for one solution puzzles. And finally, the DFS is used to determine if a graph is bifurcate or not. Okay. Now coming to the algorithm part, the set status equals to 1 ready state for each node in G. Step 2 will be push the starting node A on the stack and set its status equals to 2, waiting state. Step 3 will be repeat steps 4 and 5 until the stack is empty. The step 4 will be pop the top node in, process it and set its status equals to 3, process state. Step 5, push on the stack all the neighbors of n that are the ready state and set the status equal to 2, waiting state, exit. So finally, the spanning tree. So we will discuss the spanning tree and the minimum spanning tree, but we have already discussed the graph, the undirected graph, the connected graph and directed graph. So in case if you have missed any details about the graph, then you can go you can back forward and watch those videos and watch the video so that you can understand the graph and the types of graph, which are undirected graph, connected graph, directed graph, etc. Those are only 3 graphs, I must say. So please kindly do memorize that first, then come to the spanning tree. So what is a spanning tree? A spanning tree can be defined as the subgraph of an undirected connected tree. It includes all the vertices along with the least possible number of edges. If any vertex is missed, it is not a spanning tree. A spanning tree is a subset of the graph that does not have cycles, and it is also called cannot be disconnected. A spanning tree consists of n-1 edges, where n is the number of vertices or nodes. Okay, so all the possible spanning trees created from the given graph, which we can say G, would have the same number of vertices, but the number of edges in the spanning tree would be equal to the number of vertices in the given graph. Okay, so coming to the applications, basically a spanning tree is used to find the minimum path to connect all nodes of the graph. Some of the common examples of the spanning tree are cluster analysis, civil network planning, computer network routing protocol. Okay, so then the application, if these are the applications of the spanning tree, and the application of minimum spanning tree will be the minimum spanning tree can be used to design the water supply networks, telecommunication networks and electrical grids. It can be used to find the path in the map, and the algorithms for minimum spanning tree can be found from a weighted graph by using the algorithms given below, Prim's algorithm and Kruskal's algorithm. So first of all, let's understand the Prim's algorithm. It is a greedy algorithm that starts with an empty spanning tree. It is used to find the minimum spanning tree from the graph. This algorithm finds a subset of edges that includes every vertex of the graph such that the sum of the weights of the edges can be minimized. And coming to the Kruskal's algorithm, this algorithm is also used to find the minimum spanning tree for a connected weighted graph. Kruskal's algorithm also follows tree approach, which finds an optimum solution at every stage instead of focus on a global optimum. Okay, so these are the parts of graph and the types of graph. So I have explained it as much as possible, and if you guys have confusion in some of the part, because I know that in case of AVL tree, in case of this one, the adjacency matrix, right, sequential, in case of graph representation, or in case of BFS algorithm, if you guys have some doubt, then you can just rewind the video. I can check that later. And if you after watching the video, if you guys still have doubt, then you can definitely consult Google or YouTube, okay, or other channels, in case if you have misunderstood anything. Okay, so I will meet you in the next video. Till then, bye bye.